Hello, my name's Tom Hadfield. I'm a doctoral student in the Protein Informatics group in Oxford. I'm going to tell you today about the work I've been doing with deep generative models for fragment elaboration. So my project is based within fragment-based drug discovery. And for those of you who've never heard of that before, it's a two-stage process to design a drug where you start with a fragment library, which is a collection of very small molecules, and you screen them against the target you're interested in and collect those that bind with weak affinity. And then in the second stage, you attempt to improve the binding affinity of those by appending structure to your fragments to end up with a high affinity binder. And currently the second stage, with the fragment to lead stage, is done in a very ad hoc fashion, is quite expensive and time consuming. And so there's a real need for tools that can help speed up that process. There's been a bit of interest in this area in the last few years using deep learning methods for fragment elaboration. And up till now, those methods are either entirely ligand-based, which is to say they're not interested in the protein at all. They don't have any kind of protein-specific information, or they encode information about the protein implicitly through the use of known active molecules against that target. And there aren't any currently available fragment elaboration models which derive that information directly from the protein, which is what you need to do if you're working on a novel target for which there are no known actives. And that brings us around to the method we're proposing, STRIFE, which stands for Structurally Informed Fragment Elaboration. And that incorporates structural information explicitly through the use of fragment hotspot maps, which describe regions of the binding pocket which make a disproportionate contribution to binding affinity. And so in terms of fragment elaboration, what we'd like to do is we'd like to make elaborations which place matching pharmacophores within hotspot regions. And so to process these fragment hotspot maps, which we've got an example on the left, where the red regions correspond to acceptor hotspots and the blue regions to donor hotspots, we represent it as a set of voxels. And then through a clustering and filtering process, it all boils down to a small set of 3D coordinates for the pharmacophoric points. And our aim is that we'd like to place a matching pharmacophore in close proximity to one of these coordinates. So our generative model takes a fragment as input and a pharmacophoric profile vector, and it adds atoms to the fragment whilst keeping the original fragment fixed using the constrained graph variation autoencoder framework. And the pharmacophoric profile vector allows you to control what kind of elaborations you make. And it comes in two different settings, a coarse-grained or a fine-grained vector. With the coarse-grained vector, you simply specify how many of each kind of pharmacophore you would like to see in your elaboration. So you might say you'd like 2 hydrogen bond acceptors. Whilst in the fine-grained, you still say how many of each kind of pharmacophore you want, but you also specify how far from the exit vector you'd like to see it. So for instance, you might say 2 hydrogen bond acceptors, one being 2 atoms away from the exit vector and one being 6 atoms away from the exit vector. And that really gives you a very high amount of control over the kind of elaboration you produce, while still allowing you to create a diverse set of molecules. So the sort of schematic of STRIFE is on this slide. It's a 2-stage process. So in the first stage, we like to explore lots of different elaborations in the context of the binding pocket. And so we've got one of these pharmacophoric points that we've processed from a hotspot map. And we use the coarse-grained pharmacophoric profile vector as an input, and we generate lots of different elaborations of lots from different kinds. And remembering that our goal is to place a matching pharmacophore close to a pharmacophoric point, we measure the distance between each pharmacophore and the pharmacophoric point after docking it in gold. And then we keep those ones which have managed to place a matching pharmacophore very close. So like, for example, this one here. And what we do with those is we use them to derive a fine-grained pharmacophoric profile, very similar to the way that current models use known actives to derive that kind of pharmacophoric profile. We're using these sort of quasi-actives to do so. And then hopefully, by being able to have a lot more control over the elaborations we're producing through the fine-grained profile, we can generate elaborations which will consistently place a pharmacophore close to the pharmacophoric point. And so we did some experiments with our new model on 74 fragment ground truth examples derived from the CASF set. And we compared our model to an existing structure unaware model developed by Aros Boussonol, sort of reinvent scaffold decorator. And we computed some basic stats, the proportion of valid, unique, and novel elaborations, and also we took the top 20% of elaborations, computed the standardized ligand efficiency of those elaborations, and compared that average to the ground truth. And we did that for all 74 examples. And so a positive delta SLE implies that the top elaborations being made are more efficient than the ground truth, more ligand efficient than the ground truth, whilst a negative delta SLE implies that they're less ligand efficient. And we can see that STRIFE managed to, on average, create more ligand efficient elaborations than the ground truth, which we're quite happy with. So yeah, that's it. Thanks for listening. Acknowledgements to all the people who've helped me develop STRIFE, the Oxford Protein Informatics Group, and my industrial partners, Roche, UCB, and LifeArc. If you're interested in finding out more, please come and talk to me at one of the poster sessions, and see you at the conference.